Okay, so last time we constructed the most fundamental and important um, mathematical structure or mathematical object that we will be employing throughout the entire course and the entire theory itself. And so last time we constructed FE. Okay, so we did construct FE, which is this ordered pair, which is basically, if I remember correctly, it's E. This is the free group over E. By E dot Y Z. Okay, so FE. And this is just a group presentation of the entire structure. The actual structure is this. So it's the free group over E, English alphabet, or the ordered English alphabet. Where E, of course, is composed of an ordered set, A, B, double dot, Y, Z. Okay. So we constructed this last time. And yeah, sorry if my bird keeps screeching. One of them just passed away lately, and I believe that the remaining one is grieving, so I do apologize if you guys hear screeching in the background. Okay, so So we constructed this, and we needed this because we wanted to mathematically formalize the definition, or mathematically formalize the word cube. The reason why this is important is because if your crush has a name that contains English letters inside it, then their name is an element of F sub E. And likewise, the word cute is an element of FE, and that's why this structure is very significant. Okay. Right. So, so for this lecture, for today, what we're going to be doing is we're going to dive straight into our theory and construct the first theorem. I'm aware that in the paper, the first theorem concerns modal logic, but we're gonna start with group theory because I think that's one of the most I believe elegant. Not really. I don't think the elegance of something in math is subjective, but for me it was an elegant thing to come up with. So we're gonna use group theory to prove that your crush is cute. Just go for today. Okay. So the first thing we're going to do is let S be a collection of symbols, or a set of symbols. Okay. And next thing we're going to say is that cute is inside this set. And then, obviously, name, or the name of your crush, is inside this set. And every other element, including these two, are going to be abstracted, or you can say indexed by a family of new symbols, p sub I, such that I exists inside some index set j. Now, j can be the integers. In fact, in our example, in our theorem, j will be the integers, or some other set. So j could be the naturals. Okay. But the thing is, when we say j is the naturals, and we try to construct a group out of S, right? Excuse me. When we try to construct a group out of j, if it is n, then it's not quite going to be close, so it won't become a group. I mean, it could be a groupoid at least, but not really group. Okay, so I mean, not really groupoid. It could be a magma, but yeah, I mean, magma is the same term as groupoid, but yeah. Our ideal set would be integers. Okay, so alright, so far our set S will be something like this. If we let J be the integers, or our index set be the integers, S would look something like this. So open brace, a string of ellipses to denote a bunch of new other elements to make sure it's closed. And then I get minus name, and then dot p sub n, and then q. So minus p sub n, and then q. And then I want you guys to take note that this group is not a finite group. It could be an infinite group like the integers. In fact, I will show that there is a bijection here, and that proof that this set is bijective with the integers has been used a lot already, especially in that lecture I did back in femboid theory, where we showed that the femboid's mod and femboid is, isomorphic to the integers mod n. Okay. P1 and then P0 are identity element. Oh no, this is not P1. Then this is P1. Dot dot dot. Ute. Then dot dot dot. Pn. And then name. I'm sorry if I'm sneezing or my voice sounds a bit like shit. I'm kind of going through a cold, so yeah. But don't worry, my mind's still intact, so I'm able to do this lecture. Alright, so that's our set S. So this ellipsis, these two ellipses over here, just tells us that there are more elements beyond name. And a key thing that we want to say is that the cute and name here, just like any other symbol here, can be indexed as well with a p sub I. So we say that name is defined to be, so a colon, and then equal sign. So it's defined to be some p sub 2n minus 1 for some pn here. All right, and then cute is defined to be p sub n minus 1. And likewise, minus name, you guys will see why I have negative versions of these guys later. Right? P sub 2n minus 1, but this is a negative, and the negative cute, whatever that means, is minus p sub n minus 1. Now I'm making it as general as possible, which is why I placed here n. So you can plug in any number here. Let's say it's let's say Pn is 3. So therefore this would be Pn is 3 here. So therefore that would be minus p sub 1, and then minus p sub 2, then minus q, then minus p sub 3, and then you have some more a p sub 4, right? And then p sub 5, and then this is p sub 6, which is 7, no 5 I mean, which is 2 times 3 minus 1, and 2 times 3 is 6, minus 1 is 5, so it checks out. Alright, and you guys will see later why I made name name p sub 2n minus 1. Okay. So here's our setup for the set, and some key definitions here. I don't know if you guys can see it, but yeah, try not to make it so bright. Alright. So now that we have our set, this is just a set. A group requires an operation that we can do on the elements. So if we recall what a group is not just a collection of numbers or symmetries or something like that, or objects, but it is a collection of them with a predefined operation we can do on the elements. So for the integers, we're an additive group of the integers. Our operation, there's addition, and it satisfies some properties that must hold for any element inside the group. Okay. All right. So now let's define our addition operator, which takes two inputs in S, S cross S, and takes it to S. So it's a closed operation, right? It's a closed operation. It takes two distinct inputs from S and then spits out an output in S. All right. All right. So this operation is defined to be, over some piece of I and a piece of J, a single piece of I and piece of J. And I and J can be inside an index set we said, and it can be cute and named. And that gives us piece of I plus piece of J, which is defined to be, these are all definitions. Piece of I plus J. Okay. And an important thing is to define subtraction. And subtraction is if one of these guys are less than p sub 0, which is the identity. So the addition of it for p sub j less than p sub 0. So same p sub I, p sub j put into this operator gives us p sub I plus minus p sub j. Okay. And this gives us p sub I minus p sub j, which is defined, all these are definitions, which is defined to be p sub I minus j. Alright, so these are the crucial relations that needs to hold here, or the operation. This is how we're going to define it. And we've already done this so many times in the channel. I'm just applying it into here. Alright. Alright. So, alright. So what if we add name and name and cube? So what happens when we add name and cube? Well, just recall that of course I said a while ago that name is p sub 2n minus 1, and that's cube is p sub n minus 1. So that just gives me p sub 2n minus 1 minus n minus 1. And that gives me the symbol p sub n, so minus 1 minus 1 minus 2. So if I add name and cube, it will give me a new element of our S, which is p sub n minus 2. So going back to our n equals 3 case, that would give me 1. The first p sub 1, of course. How about subtracting it? Well, we just have to do the same thing, but I'm just going to negate this statement over here and turn it into a negative. So that makes it p sub 2n minus 1 plus n minus 1. So it distributes, so it's minus n plus 1. Yeah, same thing. Okay. Which gives me a different element, which is n, just n, p sub n, which is 3, the third element. Okay? So that's subtraction of name and cube, according to our define those laws. Because you're probably thinking, oh, what if we subtract and add these two? No, there it is. Okay. So with all questions possibly entertained, what we have to do lastly is to equip S with this binary operator, and we got ourselves a structure. And it's a group as well. It's closed. But there are 4 laws that a group must satisfy. The first one, so a group G, or the operator that acts on G, so G cross G to G. Alright, I'm not going to write the symbol anymore for the operation. Must have, or must be closed. So must be closed. So yeah, it maps 2 inputs and gives us out in G, not something outside G. Next, G x G must have an inverse. So every element that we put into this one here should have an opposite element or an inverse, such that when I put them together under this map, they would give me the identity element, which is the third requirement. So G cross G gives G must have an identity or a do-nothing element. And the key property of this identity element is that if I get a random element from my group or my set, and then I put it into this operation with my identity element, I should get nothing. Like nothing should happen to that element. That element should stay exactly the same. So one way of thinking about it is, if I have, say, this marker over here, and I have one element of rotation, so that means I'm going to rotate it like this. That's one element of the rotation I can perform on this thing. The do nothing element is just keeping it still, right? So if I do the do nothing element and I rotate it, it's the same as just rotating it like that. So that's the identity element. Now that's a way of thinking about what an identity element should do to another element of a group. And notice that the marker itself is not what the group is consisting of, but rather it's the rotations I can do on the marker that is part of that constitutes the group. All right. So these are the most important things that a group must satisfy. But another one that must also be satisfied is that it is associative. So it's the fourth condition. Actually, some people list it as the second one. I'm going to list it as the fourth. So G cross G out G is associative. So if I have let's say I have this map over here, and then I take in 3 outputs, A, B, C. Alright, so these are my inputs. It would be the same as performing A and B, right? Performing A and B and then composing with C is the same as, A and then composing B and C. Or composing A and B, or putting A and B first into the machine and then putting C along with that result is the same as putting B and C first into this map and then putting A in. So one way you can think about this is in the integers, or numbers in any real number actually, or just the integers. Let's restrict it to the integers. All right, I have, let's say, 1, 2, and 3. So adding 1 and 2 and then adding 3 is the same as adding 2 and 3 and then 1, which gives me the same answer, which is 5. So yeah, so addition with integers gives us a group, an additive group. Additive group because addition. Now multiplicative group is much more complicated because we require inverses, and as you know, if our identity element in an additive group is 0, because if we add 0 to any number, it just gives us that number. We can't really make a multiplicative inverse of 0. So a multiplicative inverse would be something like 1, because if we multiply any number by 1, it just gives us that number. So yeah. So so it's a group. The group axioms is what this is what this is called, the group axioms, and it's trivial to show that S here satisfies, or our group, our alleged group here, S and the addition operator we defined, satisfies these four axioms. Okay, it's trivial to show that fact, and I'll leave it to you guys as an exercise. All right. Cool. All right. So by another extension, we can say that this group over here is isomorphic to the additive group of integers. And to shorten down our notation and not make things cumbersome, I'm just going to denote this. I'm going to denote this structure as S to the plus sign. And this is usually denoted by a Z to the plus. Now the same thing happens for the real numbers. The real numbers also form a group under addition here. And in fact, it forms a ring, which is a different type of mathematical structure we will discuss in later in this theory. So the real numbers with the addition operator is also a group, and it's denoted by R to the plus. And you may be asking me, what if I try to take direct products here? How would that work? Or what if I take direct sums? Let's say like the direct sum of R and R plus. Would that make it R2 plus? Not really. What we do is just, we just use the usual notation for a group. So R, direct sum, R, and then the addition operator. So we just do that instead. We use that notation instead. Likewise with the integers, and I believe so with S. If you're that kind of person, then go ahead. And instead of making it just a single line geometrically, when we take a direct sum, it gives us a plane now, a two-dimensional thing, not really a one-dimensional thing, which is a line. All right. So to show this that the two are isomorphic, I believe this is a small lemma. It's not really going to be applicable to the theorem that we're going to do later, but it's just a nice result that we had from constructing our set. So I'm just going to replace this, and we're going to continue. Okay, so I just replace my marker, and let's prove this thing. So lemma. S, additive group S, is isomorphic to the additive group of integers. So, proof. So the goal with any isomorphism is to show a bijection between the elements of this and this, or the underlying sets. So I need to show that there exists a map, a bijection. So let phi, or phi, that maps underlying set S into the underlying set Z be a bijection. Okay, so no, we're not going to let that be a bijection, but let it be a map. Okay, so let var phi that goes from S to Z be a map. Defined to be, okay, for some piece of I, inside S, it is equal to an I inside Z. So we're basically just stating the index set here, and we're forming an equivalence relation between elements inside the index set and elements from the index set itself. So that's our map there. So the image of a piece of I inside this is I. So now you may be thinking, okay, but is that a bijection? I'm going to show you guys why it's a bijection. Var phi is a bijection. I'm trying to keep the ink as thin as possible so that I get the reserve sum. Okay, so var phi is a bijection. So Okay, so bijection is basically like a one-to-one mapping from one set to another set. Every function you can think of is a bijection. So x squared, stuff like that, it's a bijection. And it's only a bijection when given one element, or given an element in the second set, which we're mapping on, which is z here. There's only one element that we can return to in S. So if I map one element here, or if I take one element here and put it through var-phi, it only gives me one element here. And likewise, if I take one element here, put it through var-phi, it gives me one element, precisely one element in S. Okay? And it would require that both sets would have the same cardinality, and it already seems like it has the same cardinality because the index set is the integers. So yeah. So one thing to say is that the cardinality of both these sets are the same, which I'm not going to state anymore, but we will show that it is distinct, that, yeah, okay, through a contradiction. Okay, so assume, okay, assume phi maps to p sub I, the p sub j, to an element, call it alpha, okay, inside in the integers. So assume that it maps two elements onto one element. Now, what we want to say here is that these two are distinct with p sub I not equal to p sub j. Okay, so they're not the same, they're intrinsically not the same. So this would mean, under our definition of the function here, that p sub I is equal to alpha and p sub j is equal to alpha. Alright, now because they're the same they're the same with one element, by the associative or the transitive property of an equivalence relation like this, it would imply, so it implies that p sub I is equal to p sub j, which contradicts our assumption in the beginning that p sub I and p sub j are distinct. With our assumption that our stipulation is not equal. And by an extension, this would imply that this index and this index are the same. And because of this over here, it implies that two integers are the same, that even though those integers are distinct. So, to avoid cases such as 3 equals, for example, 3 equals 6, it must be that p sub I and p sub j are one singular element and the same. Okay. That ends the proof. A short one, but it's a sweet one. We're saying, what I'm saying in this proof is that I pick any two elements inside S here, and let's say that they map onto an alpha in Z. So we're assuming it's not a bijection, right? We're assuming it's not a bijection, but a surjection, or maybe you can make it an injection. I have one element here that is mapped. Excuse me. Because of how exceedingly clumsy I've been today, I accidentally broke a pill bottle. Okay. But I cleaned the mess up and we can continue. Alright, so what I'm saying here is that you can say that these are bijections. I mean, these are surjections or injections here. We can assume that, and then say, or you can probably deduce from that it would give us some cases that some elements are the same even though they're distinct. So just 3 equals 6 here. Just take I and j to be equal to 3 and 6 respectively, and you get this case over here. Yeah. And so, yeah. That's why it must be a bijection. It must be 1-to-1, unless you want this thing to happen. And so that's why it's a bijection. And the way that the addition operator carries on over from this to this is defined component-wise. What I mean by that is that we define it individually for every element. So some I plus some j translates on over to some p sub I plus p sub j equals p sub I plus j. So these two are primarily from the integers. But these now, these are one and the same elements. This and plus this and this are part of S. So the notion of addition carries on over very smoothly from here to here. And so that's why it's a bijection. They usually do that sometimes instead of a box. Okay. So now that I've proven that it's a group, now let's the last thing I'm gonna do before there's gonna be 2 things I'm gonna do before we actually do the theorem and then the proof. The first thing that we're gonna do is define an equivalence relation on the set. So we already have an equivalence relation, which is in that isomorphism between S and the additive group of and Z plus. But we're defining a new equivalence relation between 2 elements in S, given some other element in S. Okay. So yeah. So we define an equivalence relation. These 2 here that take S cross S and takes it to some new set S mod the equivalence relation. And it's defined as this. So A and B for any symbols A and B in S, okay? So it's a PI and a PJ. And it's equal to A is somewhat equal to B if and only if a new element C divides A minus B. So what I mean here is that A minus B is divisible by C with no remainder. Okay? And so we restate this by saying that A is congruent to B mod C. Okay, so this is another way of stating this here. So A is congruent, we just call this congruent to B mod C. So yeah. So now this generates equivalence class of B. It generates a congruence class of B over here. And so it's going to be defined on every element in S now. Okay, so I have a piece of J. It's congruent to some piece of I mod, and this is why I specifically define P sub M, because that is exactly what we're modding by. Okay, so P sub N, if you recall a while ago. All right. So P sub N divides P sub J minus P sub I. And how do we even define this? I mean, of course, that would give me P sub N divides P sub J minus I. But how do we define this this division? Well, it's just component-wise. Just carry this on over and say that this implies that P sub J minus I over M. So just divide the indices. Alright? And this implies that is an element of either the integers or the naturals. So it gives me a whole number. Okay, it doesn't give me a rational number or an irrational number or something like that, or a complex number. That's impossible. You get my point. Okay, and that includes cute and all that stuff as well. Alright, that's our equivalence relation. Now let's make the quotient set. Alright, let's make the quotient set, which is going to be the basis or the underlying set of our quotient group, which is the thing that we're going to be working with when we construct the theorem and its proof. So this quotient set, S mod, is defined to be the set of all congruence classes. So of P sub I, such that P sub I is inside S. And what does this exactly mean? What does this bracket mean? So the congruence class of P sub I is the set of all P sub j such that P sub n divides P sub j minus P sub I. And of course P sub j is inside S. So that's the congruence class of P sub I. And you notice that every negative element that we saw a while ago in S gets absorbed into this here. So the negative counterpart of this here gets absorbed into the congruence class of the original element. So minus cute gets absorbed into the congruence class of cute. Minus P sub 1 gets absorbed into the congruence class of P sub 1. So yeah. So now what we should get, our quotient set with respect to that equivalence relation should now be P sub 0 with a bar on top. I'm gonna put a bar here because this is not the original P sub 0. It is a symbol for the congruence class. And then P sub 1 bar, dot dot dot, lastly cute bar. Now the reason why I define cute as P sub n minus 1 is because it's the element directly before P sub n. Because once we get to P sub n, we wrap back. Alright? Once we get to P sub n, or think of it like we're traveling along each element in this set, right? We're hopping from one to another. Once we hop from cute to P sub n, we instead wrap back to P sub 0. Okay? Instead of going to P sub n, once we hop once from cute, we go to P sub 0. That's the sort of essence of this. Okay. So yeah, there's our quotient set. And now you'll notice that because of that, if you notice a while ago, that's another reason why I defined name, or name for your crush, as 2 times n minus 1, or 2n minus 1, not 2 times n minus 1, 2n minus 1. That's because it is. Think of them as being stacked. So P sub 1 also contains P sub 1 minus, right? And then this P sub 0 contains P sub n. Or this contains P sub n. Think of it like a line of elements here. And then this is dot dot dot. And this is P sub n plus 1. And if you'll notice that if I keep iterating P sub n plus 1, P sub n plus 2, just the positive here and the negative here. So this is minus P sub n. This is minus P sub 1. And the P sub n plus 1. Oh no, P sub 2. Sorry. Oh no, this is a bit confusing. Let's sort of start again. Alright, so after cute, when we wrap back here, this gives me P sub n plus 1, and then dot dot dot. Actually, you'll notice that if we iterate this up to 2n plus 1, that gives me precisely name. And likewise, negative name is also part of this congruence class, right? And that's n plus 1, minus P sub n plus 1. And then, these things iterate forever. The point is, we compactify, well, quote unquote compactify, or we shrunk the entirety of S into like this compact little set that sort of, or set of symbols that gives us like, which denotes a set, another set of all elements that are related to this one element. Okay. So that's one way you can think about it. Or you can, of course, you can think of a clock and how, even after 12, it just wraps back to 1, right? So 1 a.m. is the same as 1 p.m. But, mod 12, because, after 12, we wrap back to 1. All right. Now what I want to show next is that over there, this quotient set with an addition and a new inverse, or definition for an inverse, forms a subgroup. So a subgroup of a group, it's basically a subset of the underlying set of the original group, and the same operation, tweak it a little bit such that it still satisfies the 4 group axioms. And the only thing I need to tell you guys here is the inverse of that, equivalence relation. So for some piece of I congruent, piece of j congruent to piece of I, mod piece of n, there exists an inverse piece of I congruent to piece of j, mod pn, such that of course putting this into our addition operator gives us the identity element p sub 0, or at least the congruence class p sub 0. Okay. So there. So notice that if I plug p sub I, which is p sub j, into here, that just gives me p sub j is congruent to p sub j mod pn, which is just the same as 0 mod pn, or p sub 0 mod n. Our identity now is this symbol, right? Not the original p sub 0, but p sub 0 bar. Right? So every congruence class, or every element, every congruence class that we put into this addition here, that are polar opposites of each other, or are similar, are inverses of each other, are part of the congruence class of p sub 0, and which is why it's practically 0, or p sub 0. Yeah. All right. Lastly, the second thing I need to do is to make another definition. And this definition will abuse notation. Right? I think I didn't discuss this in the introduction, but I did say it in my paper that I will be abusing notation in order to achieve what we want here. Okay, so this definition, for any p sub I and p sub j in S, such that p sub j is congruent to p sub I, but p sub n, replace the symbol, this here, p sub j is congruent to p sub I, mod pn, with p sub j is equal to p sub I, but mod on top of the equal sign, or simply p sub j is equal to p sub I. Or in words, p sub j is p sub I. And you guys can probably now tell from this definition what our theorem is going to be, right? Or what our proof is going to be. This definition is going to be important here, and it will only apply for this theorem here, and from this section of the theory. So after we get that definition, let's finally write down our theorem, what I've been leading up to. So theorem 1, name is Q. Proof. Okay, so proof. Now S a while ago is an arbitrary one, or it has been an arbitrary one. N can be any natural number you can think of, like 1, 2, 3, 4, and stuff like that. It could even reach up to 3,000, but actually expanding the underlying set would be a pain in the ass. So I don't suggest that you make the index very large. Alright? So I'm going to define S to be the union between this set. So P sub I, such that P sub I is in the integers. So our index set is the integers. Union qt, which is defined to be P sub n minus 1. Union name which is the same as P sub 2n minus 1. And then there's also the negative versions, right? So that also implies a union of minus q. The same as P and minus 1, but negated. Union name, which is defined to be minus, or minus name, just P sub 2n minus 1. Close. Alright. Okay. Use the same exact, we're just using the same exact. Use the same exact equivalence relation, which is of course tilde, that maps S cross S, takes it to S mod tilde. Alright, S cross S to S mod tilde, giving S is equal to E sub 0 dot or the dash, okay, the equivalence relations, or the congruence classes, sorry. No, equivalence classes, not congruence classes. The equivalence classes, okay. Alright. So notice that name is an element of the congruence class of qt, which is defined to be qt dash. And according to our definition, name is congruent to qt mod pn. In S mod tilde. Okay, so that's why I said about P sub n, because that's what we want. And according to the definition, so it implies that name is equal by a mod to qt, and that simply tells us that name is qt. So end the proof. QED. Demonstrando. So there. That's our proof. And so lastly, to end off the lecture, we just say that all of this happens inside S mod this, which is defined to be in symbols S mod Pn S, which is also the same as just S sub Pn. And lastly, last footnote, this stuff, so S sub Pn is isomorphic to the integers mod n. And this is the exercise I'm going to leave you guys with. The tip is to use the lemma a while ago, okay? And the proof of that lemma. So this is our first theorem. So if you viewer are my crush, just know that I use group theory to prove that you're cute. Or yeah, you can use this for your crush, right? Just substitute name here for your crush's name. And I forgot to mention this a while ago, but just like I mentioned in the intro, I mean not intro, but the first lecture about constructing FE, if your crush has letters in their name that is not part of the English alphabet or the Latin alphabet, just make a new alphabet and just do the same construction I did in the first lecture. So I hope you students enjoyed this lecture, and yeah. So name is cute. So you were cute. So yeah, use this as like a group theoretic method of calling your crush cute. So crush, again, if you're watching this, this is a group theoretic method of saying you're cute. So this is a good place to stop.